We're working through the AB Fall multiple choice, 8 through 15 multiple choice review, final fall exam review. Number 8, we're trying to find the limit as x approaches infinity. So remember, if we're approaching infinity, we compare degrees. Okay? And if we compare degrees between numerator and denominator, notice the numerator has a higher degree than denominator. So we know that the limit, this graph is, this limit is going to go to, as we approach infinity, will either be positive or negative infinity. Okay? The way we decide between these two options is we look at what direction this is going towards. It's heading towards positive infinity, so we can choose a large representative value, let's say 100, and plug into the numerator and denominator. So this will give me positive in the numerator, denominator also positive, so positive over positive will be positive infinity. Number 9, again, approaching infinity, so we want to compare degrees. Numerator and denominator have different degrees. Denominator has a higher degree. So if you think about it, if your denominator is growing at a faster rate than the numerator, then this fraction is going to get smaller and smaller over time, and eventually will go to 0. Okay. Number 10, limit as x approaches 0 for tangent of x over x. First thing we do is we plug in 0. We get 0 over 0. Tangent of 0 over 0 is 0 over 0. So we know in determinant form we have to do something more with this problem. So we know we do have trig rules for limits. That's in terms of sine and cosine. So we can convert tangent to be in terms of sine and cosine. So let's convert tangent to be sine over cosine. Sine over cosine of x times 1 over x. I'm just pulling this x in the denominator out as 1 over x. And if I rearrange this, I can put the sine of x over x together as one fraction, and then put the 1 over cosine x as the other fraction. And once I do that, then I can visually see that we have sine of x over x, which becomes 1 because of our rule, sine of ax over bx equals a over b. And if that goes away, then we're just left with a limit as x approaches 0 of 1 over cosine of x. Plug 0 in for x, we get cosine of 0 is 1, 1 over 1 is 1, so that's our limit. Number 11, limit as x approaches 0 of absolute value of x over x. Whenever you see absolute value function, you can always think of this as a piecewise function. So there's a positive form of this, which is positive x over x. That's just the denominator is not going to change, where x is to the right of 0. Okay? And then we also have the negative version of this absolute value function, which is going to exist to the left of 0. So x over x is going to be 1, negative x over x is going to be negative 1. So basically you have two linear graphs, one that is holding steady at a y value of 1, and the other is holding steady at a y value of negative 1. And we see that as we approach 0 from both sides, it's not going to connect. So this is going to be a non-removable discontinuity, because the limit as x approaches 0 from the right side is going towards 1. As we approach 0 from the left side of 0, it's approaching negative 1. So we see that the one side limits do not agree, therefore limit does not exist. Okay. Answer choice D. Number 12, limit as x approaches infinity of sine of x. If we think about sine of x, this is what the sine of x graph looks like, right? You may think that it's oscillating between negative 1 and 1, but limit is asking, does the graph approach a specific, does it get closer towards a specific y value? And we see that it does not. It oscillates, but it's never settling on a specific y value. So because of that, we say the limit does not exist, at least not as we approach infinity. Okay. Limit as x approaches 0 of sine of 3x over 4x. First thing we do, plug in 0. We get sine of 0 over 0, which is 0 over 0, indeterminate form. But we do have a limit rule that we can use. But we do need to make some adjustments because this is not in the form of sine of ax over bx. What if, though, we multiply this term by x over x? Okay, we're introducing x into the problem, but we're not changing the problem because x over x is just really 1, and times 1 is not changing anything. But if I rewrite it, if I multiply by x over x, I can rearrange these as two fractions, sine of 3x over x, and then x over sine of 4x. Right? I'm just rearranging these terms, and these are being multiplied. The order of multiplication is not going to matter. But here, it's visually easier to see that we do have a rule here, approaching 0, sine of 3x over 1x would just be 3 over 1. Reciprocal is also true. The rule also holds. 1x over 4x will just be 1 over 4. So 3 over 1 times 1/4 will be 3/4. 14, we do have a rule for 1 minus cosine of x over x. And the rule is limit as x approaches 0 for 1 minus cosine of ax over ax is simply equal to 0. So that's not matching any of these answer choices, so none of these. For 15, we have a piecewise function, x squared minus 1 on either side of 1, and then we have an order pair of 1, 4. Which of the following statements are true? These are all dealing with limit continuity conditions. So let's just go through and step through continuity conditions. So the first condition, the point in question is at x equals 1. So we want to find the order pair f of 1 is equal to 4. That does exist. Okay. Next thing is find the limit. Now to find the limit, there's no need for us to do one-sided limit because x squared minus 1 is going to be the same graph on either side of 1. Okay, so to the left of 1, approaching 1 from the left side is x squared minus 1. Approaching 1 from the right side of 1 is also x squared minus 1. This function is not split into two branches like, for instance, when we wrote this problem out, where we have two separate functions on either side of our target x value. Here, x does not equal to 1 just means that this curve applies on both sides of 1. So we don't need a one-side limit. We can just simply find a limit of x squared minus 1. So first thing we do, evaluate limit, plug in the x value. So 1 plugs in for x. 1 squared minus 1 is 1 minus 1, which is 0. So the limit exists at 0, but the order pair is at 1, 4. So we see that the third condition is going to fail. 4 does not equal to 0. So what happens is the limit exists, the point exists, but there's a removable discontinuity. There's a hole in the graph, and that hole means that the function is not continuous, so this statement is false. So the only true statement is going to be the point exists and limit exists, so answer choice C.